Share my screen. Let's try that. Okay, in theory, you guys should be seeing my screen and hearing my voice. Is that actually happening, Grace?
Yes, sir.
Outstanding. All right. So, couple of, as everyone trickles in here, couple of reminders. Big one is obviously lab is due today. The second one is a reminder that after today, I'm going to be gone for about a week and a half. Captain Forbes, who's the assistant course director, is going to take over my classes for me because my good lady wife is having a spinal surgery on this Thursday. So I will be there for that because it turns out, as much as I like you guys, I like her better. And then Kevin Forbes will be here for the next week and a half doing that. He will make sure that you guys get any help you need on anything, including the quiz, which is next week. So lest you guys thought that somehow because I was not here that you did not have to do that quiz, that is definitely not the case. So make sure you are ready for that and get that knocked out. And then I promise I will come back and finish off the course with you. I even asked Captain Forbes to, only do a moderately good job so that you guys would definitely miss me while I am gone. That said, after I am done today, I will post up today's lessons as well as the code, and I will go ahead and post videos of lessons I would have given over the next couple of days, as well as the code. Not because you need to look at them at all. You'll still have Captain Forbes, but I know he does not post the videos to YouTube, and sometimes you guys want to use my stuff. So I'm just giving those to you guys as additional resources. It is not me passively aggressively trying to say his stuff is not good enough. I just want to make sure that they are all up there. They will be videos, probably the videos of the lessons will probably be from last semester, so I will double check to make sure that there's nothing that has changed. And then if you see me talking to cadets in there, it's because it was last semester. It was not that I did a whole theater monologue with actors just for your guys' benefit. I don't care about you that much. Okay, before we get into today's stuff on least squares, anyone have any questions about admin or what's going on or what has happened or what's going to happen here for the next couple of weeks? Awesome. Okay, so I'm going to try to talk a little bit more today just because it's my last day to do so before I leave, and I want to hit some of the concepts. We are now actually doing the linear regression in R, and like I said before, R is going to do all of the heavy computation lifting. It's only really 2 lines of code that you need to learn today. And so what I want to spend more time on is why we're doing it and being able to explain it, because that's, since you don't have to do as much computational work, you are going to be more responsible for understanding what's going on under the hood. So if I say something and it doesn't make sense, please interrupt me to make sure you do understand. Okay, so quick summary of what we were talking about last week. We were looking at this make-believe relationship between grades on your final and total years in the Air Force. And I wanted to foot stomp again the difference between a couple of equations, right? This is the real equation, the mythical, theoretical one that we will never actually be able to find out, right? Where that's the actual response variable. This line in the middle with these beta coefficients that do not have hats, this is saying the actual, this would make a line showing the actual average response of all possible variables. But even then, even if we knew that, which we never will, there's still this error that's normally distributed, right? That for any given point, even if I could predict exactly what the average score is for something, there's still going to be normal error adding a plus or minus to it to show that, yes, even if this was the real average, which it wasn't, the real values are going to be distributed according to a random variable above and below it. So what we do, since we don't actually know anything about that, is we take a sample, right? And so we get a sample of a bunch of X points and Y points that are ordered and paired together so that we have I would say X sub I, Y sub I is my ith sample pair. And with that, I can then create this equation down here, right? And I can say Y hat I, which is my predicted Y variable, my predicted response for Xi, and that is going to be according to this equation where it is my estimated intercept plus my estimated coefficient times my real X variable, right? I'm still using the real X variables to estimate where my Y is going to be at, right? And that equation is my best fit line, right? If I put in a Xi, I get a Y hat I. In general, the equation for that with those hatted coefficients is my best fit line. These are the real ones. I will never know. And so by estimating it, I get this best fit line. And that is what this best fit line, this least squares regression, linear regression line, is where that comes from. So anything conceptually on this screen or mathematically that is not making sense to you guys, or that you would like me to try to explain better? All right. Okay. So creating this line is easy. It is literally a two-letter function in R, LM, for linear model. A bunch of you guys actually already did it on Lab 7, even though I didn't ask you to. You made a regression model for the data. So we'll get into that in a second. What's more important is, since that's so easy, what I need you guys to do is understand we have conditions like we've done on a lot of other things before, right? These are the conditions for a least squares line. Now, that said, it's not like if these don't fit or these aren't met, you can't do it. This is America. You got freedom of speech. You can do whatever you want. You can do a least squares regression on anything. It's just a question of, will it actually be useful or mean anything, right? If I have data that looks like this, right, I can do a least squares regression on it, and I'm going to get a line that looks like that. Obviously, that data looked like it was parabolic. I can do a least squares regression. It's just going to suck, right? And so we want these conditions to be met at some level to say whether or not our least squares is appropriate, right? And without going into the math of them, these four things, basically linearity, it should look like there's a line, right? If it looks like anything else besides a line, we shouldn't be doing a least squares regression. The second one, the residuals should be nearly normal, right? Going back to this slide, we said, hey, the real equation that we'll never know, we assume that there is a normal distribution of the data above and below, right? So we are assuming that when we look at our line, that our sample residuals should also be about normally distributed to match that assumption of the underlying distribution. The third one is constant variability, right? So constant variability is saying that I expect it to be around that line about constant variance. They shouldn't be, I think someone actually brought this up last time. I shouldn't see all the dots clustered around my line at one point and then spread out at the other. If something like that happens, then that should be an indicator that there's something going on with my data that maybe requires further investigation. Maybe that's actually two subsets of data in there that would be better represented with two models, or maybe I should cut out some of the data. But the point is that for it to be a respectable model, I should expect that variation to be relatively constant around the line. And the last thing is a condition we've been using in a lot of our tests up to this point, that the observations be independent, right? And so it is basically saying whatever our observations are, one observation should not give us additional information about the other one, right? Or they talk about it doesn't have to be time, but they talk about time a lot because that is a common source of non-independence, right? If I take a random sample, if I'm trying to measure how long you wait at a red light at the intersection by my house, and I take random samples throughout the day, those observations aren't going to be independent because I know that if the observation is earlier in the day versus later in the day, the wait time is going to change based on whether it's rush hour or not, right? So there's this additional variable of time that is giving me extra information. And so that is just one example, but it is something we have to check for. A lot of times we say things aren't independent because the data, like I said, there's certain parts of it that should be divided up or taken out of. But these are our four conditions. Now, the nice thing is, once again, R is going to do the heavy lifting. We have a single line of code that is going to generate charts that have the information we need to check every one of these conditions. So you need to be able to run that line of code, but it's not hard. It's 4 letters instead of 2 letters. So hopefully you guys can handle that. But because that part is easy, it is going to be more incumbent upon you guys to understand how to read the charts to know whether or not these conditions are met. So that's what I want to spend the rest of a little bit of time on here going over those. So before we go into those charts and how to read them, do you guys have any overall questions about what these conditions are and what they mean? You guys missed it last section. I did not realize how insulated my mug was and how hot my coffee still was, and I almost died on camera. Okay, or at least burned my lips. All right, so the first one is this condition of linearity, right? And so on each one of these pages, I'm going to show you 2 charts. They're the same chart. This is the chart to check linearity. And this is what a good one would look like. This is what a bad one would look like, right? And I'm stealing these pictures from, in your guided lesson, there's a link to the University of Virginia where they talk about these exact conditions and what the checks look like. And so I would literally go as far as to bookmark that and keep it somewhere because it is a awesome quick reference to remind yourself of what these conditions mean and how to check them, right? So the first one is the data linear? And we use this residuals versus fitted plot. And basically what we're looking for is the plot's going to have this red line, and we want that red line to be basically straight. I realize that line on the left is not straight exactly, but for our conditions, that is basically straight. What we don't want to see is a pattern like this where it looks curved, or maybe it looks sinusoidal or something like that. The point is we're looking for, is there a pattern in our residuals? If it is relatively straight, then we say the condition passes. If there's any kind of nonlinear trend, then we say that condition does not pass. Questions? All right. Next one. This is for nearly normal. Now, when we've talked about whether or not data is normally distributed before, we usually have been looking at histograms, and that's totally fine. But the plot that this puts out is what's called a QQ plot, which some of you may have seen in the guided portions of the lab. But it basically stands for quantile, and it's saying, it's hard to see on this picture, but there's a line right here and a line right here, right? And that is the line of saying, if the data was normal, here is where the dots, your observations would be. And then the actual circles, those are your actual observations. And so the more your observations stick to that line, the more normal they are. So on this side, even though I've got a little bit of a wiggle right there, and overall it's kind of a little up and down, overall it sticks pretty closely to it. So this would be a definite pass for normal. Whereas something like this, where it is curving away from that line pretty dramatically, that is a case where that is the normality check does not pass, right? And to be clear, we're looking at the residuals here, right? They're saying we're looking at the residuals of our graph and saying, are the residuals normal or are the residuals not normal? So that is how we would, this is the plot we use to check whether or not the residuals are normally distributed. Any questions on this chart and how to read it for this condition?
Sir, so is there like a certain amount that it can be off by and it's still like reasonably like
Sure.
normality, like dependent
So
on like which test?
yeah, so I wish I could tell you like, hey, here is the angle, and if it's off by this, it's good, and if not, then it's not. Unfortunately, this is, I hate the phrase. I'm not going to use the phrase. It's more of an art than science because it's not, and that's stupid. But there is no 100% right or wrong answer, right? The purpose of these checks is to look at it and make a judgment and decide. You know, if you're worried that it's not exact, then say, hey, there's, you know, if you saw this chart and on a lab and you said it seems mostly normal. However, on the lower left side, it starts to curve away and back, and so that might warrant further investigation. You'd be allowed to say that, and you would still get full credit on it, right? What I wouldn't do is put a chart like this on a test and say, does the condition pass? Yes, no, right? If I was giving a hard yes, no question, I would make the question, make it, you know, very obvious, where this would be, you know, something like this, or something where you didn't have to make a call, right? But yes, in general, sometimes it is not 100% obvious, and you just need to do your due diligence and say what it is. So I know that's not the perfect answer, but usually the best thing I can say is I usually look for things where it is far away and stays far away, right? If I saw something that went like this, like I might be a little more okay with that because it goes farther away, but it's staying on average to here, where here it is literally, you know, going away and not coming back, which again is not the perfect answer, but that really goes back to when you write it, your answer is not going to be yes, no, it's going to be yes, the data seems to stay close overall to it, or you know, normality does not appear to hold because it curves away, or if you wanted to say on here, it seems mostly normal. However, there is some variation near the early values that is worth investigating. You just have to show that you're doing your due diligence and making your best call.
So this is more of a question about the lab. So I did the QQ plus check for normality for
Mm-hmm.
ANOVA, but I ended up getting something that looked more like case two. So
Okay.
I said like, okay, this is kind of concerning because we can only say that this is very, very roughly normal,
Yeah,
not that it's actually.
and that's a perfect response, because in the real world, that's the type of terminology used. Is like, hey, this is concerning. Basically saying, hey, you might have more information than I have. Based on the information I have, this seems very roughly, and I can still do it. But you know, you're basically saying, before you spend $2 million on my analysis, it might be worth $1,000 to get another sample and see if we can get this better.
Yes, sir.
Good question. This is what drives math majors crazy about stats, is the idea of, they go, so what is the correct answer? What's the mathematical pure equation? And I have to say, well, it varies, and you got to, you know, use your best judgment. They go, no, I didn't become a math major to use judgment. I became a math major because I want to follow rules and have an equation that tells me what is true all the time. And I go, no, I'm sorry, you got to use your judgment and your brain. And they go, screw you, I'm going to go take stats math 377. And I go, okay, that's cool, we'll talk later. All right, any other questions on any of this? All right, the third one is the constant variability, right? And so the idea here is that we want to see a relatively equal variation throughout the entire set of residuals. So here I have it, I want to see basically that red line and basically a shotgun blast of random above and below, right? So, and everything is about the variation similar above and below. This one is a bad example because it starts out very close to the line and then gets further and further away from the line as I go, right? I could also have had it where it started out far away and then got close and then far away, something like that. But the point is that I'm looking at the variation and I want to see random constant variance above and below that line. I do not want to see any patterns about how close the residuals are from that line. Any questions on the constant variability? All right. The last one is independence. Now, independence is a little tricky because we tend to get in a bad habit sometimes of misunderstanding what independence means, right? At its very basis, when I talk about independent observations, what I really mean is if I have observations are independent if knowing something about one observation does not give me information about the other observation, right? So, for example, if I had a sample data set of cadets' scores on finals that they of all finals they've taken at USAFA, that data wouldn't necessarily be independent, right? Because there could be observations in there from the same person of different finals, right? So I might have Cruz's score on his Calc 1 final and his score on his Calc 2 final. And those aren't independent because if I know how well he did on the Calc 1 final, then I probably have a pretty good idea of how he did on the Calc 2 final. There's a relationship between them. They're not independent, right? So that's what it really means to be independent. Now, up until this point, when we've talked about samples, we've usually said if the sample is a fully random sample, we can usually assume that the data is independent because if it's random, they don't have any connection, right? But that doesn't necessarily mean it can't be have problems with independence because in that example, if I took every cadet's score on every final, and then I randomly selected 100, it's still possible that I would have two scores from the same person, and therefore it wouldn't be independent. So while a sample being fully random is usually a good way to check if it's independent, and if it's not random, it's not independent, and if it is random, it usually is independent. It is not a one-for-one check. Same thing that we're going to do here. We still have the basic definition of independence. However, when we are doing a least squares regression, the biggest issue about independence usually comes from outliers, right? It's the idea of if I see data that looks like, let's say, something like this, and I have an outlier up there, usually what's happening is that outlier is an outlier because it's not independent from all the other data, right? Something is happening there that is causing that to be an outlier, and it is different than the rest of the data, right? So usually outliers are an indication that we have an issue with independence. So these diagnostic plots are not explicitly checking for independence. They are checking for outliers that are so egregious that they are tilting our line in a way that we should be concerned about, right? And so you don't need to know what Cook's distance is, but basically the way we read this plot is we look at all the plots, and if they are all within Cook's distance, then we say, hey, we don't have any outliers that we have to worry about. Cook's distance is this line here that is going up here and down here, and this is outside of Cook's distance. Because it's outside of Cook's distance, we say, hey, this thing has an outlier that is outside of Cook's distance, and so it is so far from our data, it is messing with our line. And so that is going to lead us to believe that there may be an issue with independence. So going back to what Steven said before, the downside is this plot is not saying it's definitely independent or it's definitely not independent. It's just saying there is an egregious enough outlier that we should investigate further to see if this outlier is violating independence and maybe it needs to go. Now, on this condition, we don't have any outliers. Doesn't 100% mean that it is independent. We still have to use our brain and say, is there anything about this data that would lead me to believe that it's not independent? But the main source of issues of independence, which is outliers, is something I don't have to worry about. So when I say this passes, I don't say, and the plot is inside, so therefore it's independent. I say the plot checks out, which means I don't have any extreme outliers I have to worry about for independence, comma, and then I can say, and the data is random and I have no reason to believe that there's independence issues, and that's my full check on there. So that was a little bit on a soapbox down the rabbit hole on there. I apologize, but any questions about this plot or any of the other plots? Okay, then let's switch over to some code for this. Jacob, can you actually see what I've got on the screen? R-wise, I mean.
Yes, sir.
Cool. Okay. So I'm not going to solve like a scenario here or anything like I normally do. I'm just going to kind of show you. This is because linear regression is getting into a lot of the stuff that I would do in real analysis, like what I would do in my actual job, right? And so a lot of times you're just given the data and said, hey, what can you figure out from this, right? And so this is kind of an example of what I might do. First I would bring in the data. So this data is GR1 and GR2 scores from last semester. Then the next thing I might do is like, okay, let's just randomly explore the data to get an idea. Let's say I don't know anything about GR. So the first thing I might do is just do a summary and say, okay, that's just random identifier data about the cadets. I don't care about that. GR1 looks like they range in general from the high 30s to 100. Looks like the average for GR1 was the high 70s, and the average for the GR2 was the high 60s. So it looks like in general they went down. This is just going to give me an idea of what scores look like, right? So yes, this looks like it's a 100% scale like normal. Then I might try to visualize it. We've done this before. I'm going to make a histogram of GR1. Now it makes it easier to say, oh, you know what? This data is left skewed. And it looks like there's kind of a gap there in the middle. Let me see, what does GR2 look like? Yeah, it also looks like it's left skewed and has that gap. So in general, it seems like it's following a similar pattern. I might then say, well, we've talked about differences before. Maybe I'm curious of making a histogram of the differences, right? And by looking at this, I can see pretty easily, it looks like in general, the differences are more normally distributed, but the mean is a negative, right? Which means that in general, people did worse on the second GR than they did on the first GR. Although that's not, 100%, but that seems to be where the average is. Now we get to the linear regression, right? This is the money line, right? Because the next thing I want to do, if I want to say, is there a relationship between GR1 and GR2, right? Because that's something I might actually care about, of saying, hey, if there's a relationship, then maybe I can predict your second GR based on your first GR and decide, how much help you need. So I'm going to do this scatter plot. And remember, if I do a scatter plot, which is just plot, I put what I want is my Y first and my X second here. And so when I look at this, without any math, I'm going to say, yeah, that looks like there's a moderate positive linear relationship. As GR1 scores go up, GR2 scores go up, right? And so to then take the mathematical leap and do the create the regression line least squares, it is this right here. And I told you it was 2 letters, right? It's LM. LM is linear model. And I'm setting equal to this GR model so I can use that later. But it's basically say LM, and then I say I want to predict GR2 with GR1 using my data set, right? And just like with the ANOVA, if I just said this, it would do it, but it wouldn't tell me anything. So then if I say, now give me a summary of that, it will give me the summary of what it did, right? So it says, hey, here's what you told me to do right here. Do that linear model. And now it is giving me down here a bunch of information. We'll talk more about this in lessons to come. But right now, this is the column that I want to focus on, this estimate, because this is the 2 coefficients that I need in my equation, right? We showed on that first slide today that the equation is y hat equals beta naught hat plus beta 1 hat x, right? And that's what these two things are here. This says intercept. So this is saying this is the model's estimate for what my y-intercept is. GR1 is my x variable, right? Because that's the x variable I'm using to try to predict GR2. And so it's saying this is my estimate for the coefficient to go with that x variable, to go with GR1. So let me ask in class here. So Cam, are you on? Are you listening to me?
Yes, sir.
All right, so if you had to, could you give me your best shot at explaining in words with this scenario, what does 31.2326 actually represent?
Is that like the average or like the estimated, like the y hat value?
So yeah, so 30, yeah. So it's telling me that is the estimate for the intercept of my regression line. So what does that mean in terms of our scenario where I'm looking at this data and I just built a regression line. So what does 31.2326 mean in that as my estimate of my intercept?
Like the score on GR2?
It's my score on GR2 if what? And I know we're playing a little bit of guess what's inside my head. I have no doubt that you understand this, and I'm just phrasing the question poorly. Because what we're saying is, we're saying that because this is my estimate, what we're saying is that it just made up a equation for the regression line and saying it is 31.2326 plus 0.48x. That's horrible handwriting because my screen is not down. But that's where these are going into my equation. So what in the scenario where I am is GR1 here and GR2 here, because that's what I am trying to make my line for. What does that 31.2326 represent?
I don't know.
That's totally fair. I have had more coffee this morning than you have. And again, I am probably phrasing it poorly. But what it is saying is that is, since that is my y-intercept, I am saying I am predicting that if you, according to my linear regression model, if you get a 0 on GR1, then we are predicting that you will get a 31.2326 on GR2. Does that make sense? And I'm guessing also that something you already knew and just didn't realize I was asking?
Yes, that makes sense.
All right. Now, the other thing I will say is that is mathematically what that means. It's probably not too accurate, right? Because when I look at my data here, no one ever got a score on GR1 less than about 40, right? So yes, I'm going to make a line, right? If I that is my regression line, but getting a 0 on GR1 is far below anything I have a sample for, and so that is what we call an extrapolation. And so I don't actually know. I don't have any data of what people do when they get 0. So that is probably a bad guess. I need that in my model to define the line, but it is probably not accurate to say if someone says, hey, what do you think they will get on GR2 if they get a 0 on GR1? I could say, well, the model says 32, but I wouldn't trust that because that is an extrapolation rate way below where my sample is. All right, so let me follow up with, let's see, how about Ryan? Ryan, are you online?
Yes, sir.
So same idea. What does in this scenario then, what does that 0.4829 represent or mean in this scenario?
It would be
like how much they vary?
I mean, I'll give you algebraically, it's the slope of my line, right? But in my scenario, what does that mean?
It's how much the x value changes, or the y value changes per change in x.
That's exactly right, right? Or to put it a different way, it is saying, according to my model, I am predicting that for every additional 1 point you score on GR1, you will score an additional 0.48 points on GR2, is basically what that is meaning, right? Okay, we'll talk about what the rest of this table means and everything else later, but I want to get on to the diagnostics, right? So this right here is how we call the diagnostics. Actually, this right here is all I have to do the diagnostics. GR model, if you'll remember, that's what when I made the model, I saved it as model. And the nice thing about R is if I just say, hey, plot that model, it knows that what I'm saying is it goes, oh, you want to see all 4 of those diagnostic plots to check your 4 conditions, right? And so when I run that, I get all 4 of them. You don't need to do that, but what that does is, hey, it tells R, I'm about to make several charts, show them all in a 2x2 grid so I can look at them all at once. So if I didn't do that, it would just show all 4 of them and I'd have to tab between them. But this makes them easy to look at all at once, right? And so these are the 4 diagnostic plots that we use to check our 4 conditions. So starting in the upper left, I can say, that's my linearity. The red line is relatively straight. Linearity checks out. The next one is the normality QQ plot. That looks like it's following. I might say, hey, there's that 0.67 on the far right that is varying from it, and it varies a little bit at the bottom. But overall, it seems to hug that normal QQ line pretty closely. So I'm going to say my normality condition is met pretty strongly. The lower left one, the third one, that is my constant variance. Just so you know, in the book and some of the videos, sometimes they call the constant variance. Another term for this check is called heteroscedasticity. If you just want to sound like a statistics badass and use cool words, but it's constant variance. And so when I look at that, I go, yeah, it looks like it's mostly good. On the far left, I have 1 or 2 dots that are close, but I'm not going to count that as breaking constant variance because I only have 1 dot. Maybe if I had more samples, it would show the constant variance. And so I'm not going to say that that is a pattern of type variance and then moving out. It's just a lack of data points. So I'm going to say my constant variance passes. And then the last one, I can look at Cook's distance, which is actually outside of that, and say all of my points are within it. So I do not have any outliers that I have to worry about impacting independence. The only other thing I might, so I've got that, and I could say, hey, did this come from a random sample? Not quite. This was one class's worth of data, and so there may have been something happening in 2020 that didn't happen for the rest of Math 356. And so perhaps the sample is not completely independent and is not completely random. I could probably move forward, but it might be worth investigation later is what I would say. Any questions about reading this diagnostic or the judgments I made for this particular data set? The last thing you might want to do is, now that I've got that model, I can replot my scatter plot, but with my line on there, right? So this is the code again that just made the scatter plot. The line, again, once I have that linear model saved, R knows what to do with it. So if I say, hey, you do an AB line, but of GR model, then it knows what I want it to do is to draw the line based on the model. So it will draw an AB line and load up the coefficients from that model to make the line where I want it, right? So now when I look at this, I can say, yes, that looks like the best fit line of there. And I can, the rest of this code, you can look at it on your own. It's just me showing how to put other things, on there, like saying, oh, hey, now I can draw the best fit line and the GR equals GR2 line to see how the best fit differs from the GR1 and 2 being exactly the same. I can see, obviously there's a big difference, right? But importantly, this is the main takeaway. Load the data, explore it, create the linear model, understand what it means, run the diagnostic plots, understand how to read them to know whether or not your conditions are met, and then to draw this line. With this, then I can answer questions if someone says, hey, I got a 60 on GR1, I can say, oh, well, it looks like I am predicting you're going to get about looks like maybe 59 on GR2. Around that range, maybe we should, be concerned. If someone says, hey, I got a 10 on GR1, what am I going to get on GR2? And I can say, well, the model says you're going to get about a 30, but I don't actually know if that's true because that is extrapolating way to the left of my data. So I am not confident about that result. Any questions about this graph, what it means, how we got here? Anything that in the code you'd like to see again or that was missing that you would like to know how to do? Okay, a couple of cleanup things then about this linear regression, right? So this is not just linear regression, but this is specifically least squares linear regression. There are other ways to find this line. We are specifically doing the least squares regression, which we talked about before is you don't need to do it yourself, but just understand under the hood, what R is doing is to find that line, it's finding a bunch of lines and then saying, taking all those distances and squaring them and saying what line makes the sum of the squares of all those distances the smallest, right? So a couple of things to know about least squares regression. First of all, we already talked about this. Don't extrapolate. Extrapolation is bad, right? Based on this data, if I added a 20-point bonus problem and someone said, hey, it's possible to get 120, it doesn't mean that now you're going to spend 47 years in the Air Force, right? That data is outside of my original sample, and so I can't say that the model continues to work out there. There's a quote you guys may have heard from a famous statistician called George Box that I always have appreciated. He says, all models are wrong. Some are useful, right? Because people who are not statisticians or look at things will always love to say, well, how do you know this model is correct? Blah, blah, blah. And I say, actually, I know for a fact that the model is not correct. By definition, a model is something I made up, right? And so all models are wrong. The only reason we decide to use them is if they are useful. So if it is useful, we use it. If it's not, we don't. This model is not useful to do extrapolation, so we don't use it for extrapolation. Another thing that is always true about least squares regression is if I take my sample and I take the average of all of the x values and the average of all the y values and plot that point will always fall exactly on my linear regression line. That is a really handy piece of information if you're trying to test a line, or back in my day when you had to actually find the line manually, it was a way of finding, you only need 2 points to define a line. So it was halfway there to defining the line, of knowing that that point always lies on your regression line. Another interesting and nice fact about least squares regression lines is that when I add up all of the residuals always add up to exactly 0. So if I take the positive distance that all the points above the line are from the line, and I subtract off the distance, for all the points below, that will always add up to exactly 0. All right, and the last thing I want to talk about with the little time we have left is this concept of R squared. Hopefully you guys remember last week we introduced this idea of a correlation coefficient R, right? And we said R could be anywhere between -1 and 1, right? And we said, hey, if I have any kind of positive linear correlation, a perfect positive linear correlation like those dots would be an R of 1. If I had a perfect negative linear correlation, that would be an R of -1. So that was a measure of how well correlated the data is. Well, R squared is just that value squared. So first of all, instead of going from -1 to 1, R squared goes from 0 to 1. So I no longer care if it is which direction the correlation is going. I just care how good a fit it was, right? Because that's what R squared is. It's a measure of how good a fit my line is, right? So 0 is a horrible fit, 1 is a perfect fit, okay? The other thing, you don't need to know this equation as much. I don't care about that. But that R squared has this additional meaning. R squared tells me how much, it tells me what percentage of the variance my linear regression model explains, right? So I'm going to do a little bit of hand waviness on math. But if I had, let's say I had some perfect data, right? So I had all these dots on here, right? If I said, how much does that data vary? It actually varies a decent amount, right? Because the highest Y value is here and the lowest Y value is here. And so the value of Y varies anywhere from that bottom value to that top value, right? However, if I do a linear regression line, and it fits exactly through all those, I can now look at the residual plot, right? And say, what are my residuals? And my residuals are all 0 now because they all perfectly fit. So my residuals don't vary at all. So my residuals have vary nothing at all, whereas before there was this big variance. And so since my variance went from a high number to 0, my R squared is 1, because my line explains 100% of the variance. When I look at it on the y-axis, I go, hey, there's a bunch of variance. But when I look at it in comparison to my line, I go, it doesn't vary at all around my line. So my line explains 100% of the variance. Similarly, if I had data that was not perfect, but pretty good, and I went through again, I have this big variance of the Y when I just look at the Y, but when I look at the residuals, my residuals are much smaller, and so the range of my residuals is much smaller, and that ratio is the R. I would get an R of something like R squared would be something like 0.92, and so that would mean, hey, I reduced the variance by 92% from here into this little value here, right? So my line explains 92% of the variance when I look at the line rather than just the raw data. Okay, I was trying to shoehorn in that concept of R squared. The nice thing is R squared is something, again, that I want you to understand, but you do not have to calculate. When we go back over to our code, that was actually buried in our regression. So right here it says, hey, guess what? Your R squared is right here. So my R squared was 0.16. So actually, my model is not great. The R squared is actually pretty low. Like I said, 1 is perfect. I only got an R squared of 0.1679. So yes, I was able to do everything. Yes, all of my conditions met. But then if I told someone, they said, how confident are you in this model? I go, well, it only has an R squared of 0.1679. And they would say, oh, okay, so it's mathematically feasible, but I shouldn't be like deciding to put anybody on academic probation based on this model. Okay, in the 4 minutes we have left, does anyone have any burning questions that they would like to try to throw at me to answer now or after class? All right. Well, as a reminder, I am out after today. So if you got any questions, shoot them at me today. I'll be in for a limited amount of time tomorrow morning. But then I will probably not be I'll be away from teams at least for the rest of the week, and then I will not be teaching next week. If you have an emergency for some reason, there's something only I can do, which Captain Forbes can do a lot, but I am not going to say it's outside of the range of possibility. You guys are always welcome. My teams will be off, but you can text me directly. And it's in the syllabus, but my phone number is area code 425-330-8627, and this is recorded, so you can look it up if you need to. But if you suddenly have some emergency that only I can answer, I am not going to be mad if you guys text me. I wouldn't give you the number if I didn't expect you to use it. All right. So I will talk at you guys later. If I don't hear from you before then, I may not see you until Monday after next. So enjoy your lives weekend and quiz 5 in my absence. And I will be back, and we will end out this semester nice and strong, I promise. All right. I will see you guys then.